Okay, good morning. Let's get started. So, in the last class we were discussing about the von Neumann stability analysis, right. That is what we did not finish it. So, let us kind of continue with that. So, this is von Neumann stability analysis. Essentially, we would like to know if the time steps that we are using, the time stepping scheme that we are using would keep the round off errors bounded or not, right. Do the round off errors grow from time step to time step, or are they going to be not, are they going to be bounded. So, that is where we kind of looked at this formal analysis, in which we started off with the explicit time stepping scheme. So, this is the explicit scheme applied to unsteady diffusion. Right, and then we have said that there is a solution phi that we obtain on a regular computer, right. Essentially, this is a regular computation, and then we also said there is another solution capital phi which is obtained on an infinite precision computer, right, which does not have any round off errors associated with it. Okay. So, this is basically coming from an infinite precision calculation, and we equated the round off error epsilon as the difference between the regular computation and the one without any round off errors. So, we said epsilon equals phi minus capital phi, and we substituted little phi and capital phi into the unsteady diffusion equation, the discretized equation, and subtracted one from the other, and then found an equation for the error itself, right, found an equation for the round off error itself. And what was that? That was A p epsilon p equals A east epsilon 0 plus A west epsilon west 0 plus A p 0 minus A east minus A west times phi p 0, right. That is what we have. Sorry, this is epsilon p 0. Okay. So, this is epsilon p 0. Okay, good. So, we have an equation for round off error itself. So, this is round off error equation, right, which is basically the same equation as the governing equation for the dependent variable, right. Fine. Now, we said we have to kind of introduce a model for the round off error. And one good model is basically it is composed of several spatial and temporal components in an exponential sense. And because this governing equation is linear, we do not have to look at each and every component of the error that we have modeled. Rather, we can just look at one component of it and analyze the solution. That is where we wrote this as epsilon as e to the power I k x times e to the power lambda t. And we of course kind of are interested in the growth or decay of this round off error from time step to time step. So, what we are interested in is the epsilon at any location x at t plus delta t upon epsilon x at the current time level, right. This is we have termed this as what? Amplification factor, and we would like to have this ratio as what? Less than or equal to 1, such that our round off error either remains the same or it does not grow, right. That is what we would like. Now, if we plug in the spatial and temporal values of p, e and 0 superscripts, right, into the definition for error, we will obtain all these quantities, right. So, we said if you plug in the x and t values for the corresponding items here. So, that will be epsilon p would be what? Would be, if you plug in the values into this, p would be coming at x and at a time of t plus delta t, right. So, that would give you epsilon p as e to the power I k x e to the power lambda t plus delta t, right. And then similarly, we have epsilon e 0, this would be e I k, x would be for the east cell x is x plus delta x. So, this is x plus delta x e to the power lambda t would be t, because we are looking at the time level t 0. So, this is t, Similarly, we can plug in other quantities, which is epsilon west 0, this is e to the power I k x minus delta x e to the power lambda t, and we have one more quantity, that is epsilon p at the previous time level, that is epsilon p 0, right. This is e to the I k x e to the lambda t, that is all. Okay. Now, what we say is we kind of want to substitute all these values into the governing equation, that is this one, right. We plug in all of these things, and we of course also would like to divide the entire equation with e to the I k x e to the lambda t after substitution, and also with a p, right. So, essentially divide throughout. What is the equation we call this as 4 or something? Yesterday we called this as equation 4, I guess. So, this is equation 4, essentially plug in these values and then divide everything with a p e to the I k x e to the lambda t in equation 4, right. Now, once you do that, what is the final equation you are going to get? E to the power lambda delta t equals a east upon a p e to the power I k delta x plus a west upon a p e to the power minus I k delta x, right, plus we have a p 0 minus a east minus a west upon a p times 1, okay. That is all. This is what we got. Okay. Now, what we would like to do is we also realize that what is our, this is basically a one dimensional constant gamma and uniform cells, right, with source term equal to 0, right. Those are the assumptions we have made in order to analyze this thing. So, in that context, what is your A east? A east and A west are equal to gamma upon delta x, and A p is how much? Rho delta v by delta t. So, this will come out to be rho delta x upon delta t. So, how much would be A east by, sorry, this is A p 0, which is also same as A p. So, what will be these coefficients? A east upon A p, how much would this be? Gamma delta x times delta t by rho delta x, right. So, this is how much? Gamma delta t by rho delta x square. Okay. So, this is same as A west upon A p, right, because A east equals A west, both are the same. Then what about this last term that we have here, this guy, how much will this be? A p 0 minus A east minus A west upon A p. This will be how much? 1 minus, you have A east equals A west, this is 2 times A e by A p, right. This is 2 gamma delta t upon rho delta x square. Is that all? Right. A p 0 equals A p. So, as a result, the first term is 1, this is 1, right, and the remaining parts is 2 times gamma delta t by rho delta x square. Okay. Fine. Okay. Now, we will kind of substitute all these things back into the equation. So, that will give us e to the lambda, how much is this thing? What do we have here? E to the lambda delta t, e to the lambda delta t equals A e by A p plus A w by A p. So, both are the same. So, we can take that out, that would be gamma delta t by rho delta x square times e to the I k delta x plus e to the minus I k delta x, right, coming from these two terms, right. Okay. And then we have plus, we have this guy, plus we have 1 minus 2 gamma delta t by rho delta x square, right. That is the total value. Now, how much is e to the I k delta x plus e to the minus I k delta x? How much is this? This is 2 times cosine k delta x. So, if I were to write in a square terms, this would be cosine 2 theta would be how much, or cosine theta would be 1 minus 2 sine square theta by 2. So, this would be 1 minus 2 sine square k delta x by 2, right, that is fine. So, then this would be essentially 2 minus 4 sine square k delta x upon 2, right. So, we will plug this back into this term here, right, and see what happens. So, that is how much, gamma delta t by rho delta x square. So, equals gamma delta t by rho delta x square times 2 minus 4 sine square k delta x by 2 plus we have this guy, that is your 1 minus 2 gamma delta t by rho delta x square, that is basically 1 minus 2 gamma delta t by rho delta x square. All these things are equal to e to the power lambda delta t, right, fine. Okay. Mistakes, is it correct? All right. So, do we have any terms that may get cancelled? 2 gamma delta t by rho delta x gets cancelled. So, essentially what we will be left with? We will be left with the 1 minus 4 gamma delta t by rho delta x square times sine square k delta x upon 2, right. That is all remains, because this term gets cancelled with the 2 times gamma delta t by rho delta x square. Okay. Fine. Okay. What is the amplification factor in the current context? Amplification factor is nothing but e to the power lambda delta t, right. So, essentially E x t plus delta t upon E x t is nothing but e to the lambda delta t, right. If you plug in E I k x e lambda t, this is what remains. So, we want this guy to be less than or equal to 1, right. That means, we want modulus of this guy to be less than or equal to 1, right. That is the condition we are imposing in order to get a relation, if there any exists, between delta t, delta x and other parameters, right. So, essentially okay. So, what will be this value now? Essentially modulus of this guy. So, what is the maximum value that sine square k delta x can take? 1. Okay. So, essentially we have to look at, in the worst scenario, this will be minus 1 less than or equal to 1 minus 4 gamma delta t by rho delta x square is less than or equal to 1, right. That is what we have. So, we have 2 conditions. The first one is for the minus. So, this is 1 minus 4 gamma delta t by rho delta x square is greater than or equal to minus 1. This would give us what? 4 gamma delta t by rho delta x square is less than or equal to 2, right. That is what it gives. So, this will be how much? Delta t should be less than or equal to rho delta x square by 2 gamma, right. 2 gets cancelled. Okay. That is from the first condition. What about from the second condition? That is 1 minus 4 gamma delta t by rho delta x square less than or equal to 1. This would tell us 4 gamma delta t by rho delta x square is greater than or equal to how much? 0. That means delta t should always be positive, right. This will be the case always, right, because your delta x is positive, gamma is positive. So, this is always satisfied. What about this one? This is the condition that lets you choose delta t according to the delta x and the density and the diffusion coefficient that you have in the problem, right. So, this is the condition which we have also written down, I think, right, a while back for the explicit scheme. Okay. So, this is the condition for stability such that the errors do not grow, right. So, this is the stability condition for explicit scheme as applied to unsteady diffusion. So, it contains gamma, the density, delta x square and so on. Now, without proof I want you to kind of verify using the same analysis that both the fully implicit as well as Crank-Nicholson schemes are unconditionally stable. Okay. So, this is something you will verify later. Fine. Okay. Now, we have done this von Neumann stability analysis, but then we have also talked about this other analysis, which is the kind of the heuristic way, right. Heuristic way where we set the coefficient of phi p 0, right, which was a p 0 minus a east minus a west, right. This value should not become negative, right. We said that in a heuristic way, saying that because we are solving a diffusion problem, an increase in the phi p value at the previous time step should not cause a decrease in the phi p value at the current time step, right. So, in a heuristic sense we said this thing. If we use that analysis, we can, so we plug back what is, so from the heuristic analysis what do we want this coefficient to be? Always positive. That means we want a p 0 to be always greater than or equal to a east plus a west, right. This is what is a p 0? Rho delta x by delta t, right. Was it rho delta x by delta t? Yeah. Okay. And then greater than or equal to how much is a east plus a west? 2 gamma by delta x. So, what is the condition on delta t? Less than or equal to rho delta x square by 2 gamma. Okay. Do we get the same condition from the heuristic analysis and from the von Neumann stability analysis? Okay. But the von Neumann stability analysis is much more formal, so you can apply to everything. Heuristic is only kind of works in certain aspects. Okay. Fine. Now, of course, what do we do if we have to extend this analysis to 2 dimensions? Okay. So, let us say if we have, if you are talking about 2D diffusion, how do you model your error now? Your model for error E x y t would have E I k x x, E I k y y, E lambda t, right. You will have wave numbers in both x and y directions, that is what you would use. Now, if you proceed with the same analysis, you also assume that the cells are uniform. So, the delta x equals delta y, right, for the sake of simplicity. If you also assume delta x equals delta y and the diffusion coefficient is also uniform everywhere or constant, and there are no source terms. If you make all these assumptions and proceed with the analysis, what is the condition you would expect to get from the von Neumann stability analysis? I am just going back here so that you can see. So, this equation that we have, what would this equation look like? If you have more neighbors now, you will get a east, a west and a north, a south and so on, right. So, what would that eventually lead to? Instead of 2, you would be getting how much here? You will be getting a 4, right, and that 4 would essentially translate to an 8 here, because you have 2 times 1 minus 2, right, that will translate to 8. So, this will become 1 minus 8 gamma delta t by rho delta x square, and that 8 would again eventually lead to a 4 in the denominator, right. So, that will essentially lead to rho delta x square by 4 gamma if you have a 2D problem, okay. And for a 3D problem you would get in the denominator, how much would you get? 8 gamma, right. So, we kind of wrote a general equation a while back saying it will be gamma d 2 d gamma or just gamma d, right, where d is the dimension if it is first one dimension and so on, right. So, that is what you can do. Of course, somebody asked a question, what will happen in the context of axisymmetric, right. Now, what will happen in the case of axisymmetric? Can you guess it from here? So, what would change or what would not change? Would you still get a 2 gamma? Okay, that is for you to maybe figure out. You can now do it. Okay, so essentially in the context of 2D and in the context of axisymmetric, you have to kind of see what will happen, what will be the conditions. Okay, okay, all right. So, yeah. Oh, sorry, yeah, it will be 6 times, right? 2D gamma, it will come out to be 6, yeah, right, not 8, it is only 6 times. Okay, but okay, that kind of brings up a good question. So, the thing is, so what is in a 2D, what will be the time step restriction? This is in 1 dimensions, rho delta x square. In 2D, what will be delta t? Rho delta x square by 4 gamma. So, is delta t has to be, so you have solved a 1D problem. Now, if you want to do the same thing for 2D, do you have to reduce your delta t or you can just take the same delta t? You have to reduce, right. Now, it is only half of what you have taken in the 1D, right. That is what is coming out from the stability analysis. Okay. So, 2D problems are much more restrictive in terms of time stepping when it comes to explicit schemes. Okay. So, that is what this kind of tells us. Fine. So, the delta t is in 2D is more restrictive or it is smaller than delta t in 1D. Okay, fine. So, this as you can see, this entire process of the stability analysis works only for if you have kind of make lot of assumptions like constant coefficients and then no source terms and uniform cells and so on. So, you can clearly see the complexity if these are not met, right. As a result, we can only apply it to simple problems and for practical problems of complex in nature, we cannot really apply this, rather we have to kind of set up a simple problem and then see, and for other complicated problems we have to kind of use a kind of our experience to kind of judge what will be the corresponding delta t and things like that. Okay. But essentially you can use this in the context of splitting down a complex problem into diffusion, convection and so on, and then come up with several delta t's and then choose the delta t that is the smallest, right. Fine. Questions till now? No, this is clear, this part is clear. Okay. So, that kind of finishes pretty much about the different aspects in terms of truncation error, stability analysis, all these things that we have discussed. Now, we can move on to the diffusion equation in unstructured meshes. Okay. So, up till now we have been discussing structured meshes alone, right, but of course, we have introduced the time stepping schemes and everything else. Okay. Fine. So, let us move on with unstructured meshes, diffusion in unstructured meshes. So, I will go back to steady diffusion as of now, okay, because unsteady diffusion would kind of follow the steady diffusion and it will be very similar to what we have done. So, we probably would not do it again. So, we are looking at steady diffusion in unstructured meshes. Even in unstructured meshes, I am looking at two different types. One, we would like to call it as orthogonal unstructured, okay, and the second type is non-orthogonal unstructured. Okay. So, we have two different types. We will first pick the orthogonal unstructured mesh and see how to solve steady diffusion on these kind of meshes. Now, what is an orthogonal mesh? We have kind of or cells. What are orthogonal cells or what is an orthogonal mesh? We have discussed this a while back in the during the initial lectures. What is an orthogonal cell? Anybody remembers? Or what is the consequence of having an orthogonal cell? This also we have discussed till now, right? What is the consequence of having an orthogonal mesh? Area vector is perpendicular to the faces. Area vector is always normal to the face, right? A dot. So Aj dot. So essentially, what you are trying to say is you will get diffusion fluxes only in the direction normal to the face, right? You will not get the other component, right? For x, we were only getting partial phi partial x. For y, we are getting partial phi partial. We never got partial phi partial y in the x component and so on, right? So this was not happening because we have a area vector of the face in the same direction as the gradient, right? So the gradient direction is partial phi partial x, right? That is connecting what? That is connecting the cell centroids. So the line joining the cell centroids, if it is parallel to the area vector, that is an orthogonal mesh or an orthogonal cell, and if every cell in the mesh that you have generated satisfies this property, then what you have got is an orthogonal mesh, right. So that means the area vector of the faces is parallel to the line joining cell centroids. So when we talk about one particular face, we are talking about only two cells and the two cell centroids, right, because there is a uniqueness here, right. Every face has only two cells, right. So this, if it is satisfied, then it is an orthogonal cell, and if it happens to be there for every cell in the mesh, then it is an orthogonal mesh. Okay. Now we are looking at in the first context as an orthogonal mesh. Let me give you an example of how an orthogonal mesh looks like. Okay. So does it look like an orthogonal mesh? No? Yes? So essentially we have, let us say, equilateral triangles and the faces normals are parallel to the line joining the cell centroids. Okay. So for example, these are the cell centroids, this is the face, right, and so on. So this is an orthogonal mesh, a kind of an example, right. Right. So we have some structure like this. So this is basically an orthogonal mesh. Now you may say, is it structured? Right. It kind of looks like there is some structure, isn't it? It's kind of not very easy to generate an orthogonal mesh which is unstructured. But of course, if you have a domain that kind of ends in an irregular way, then that would be kind of an unstructured mesh, right? You don't have a structure anyway. Okay. What is the other way you can generate another orthogonal mesh? You can of course have a structured mesh, right, which is a square mesh or something, and we can partition them into triangles, right, cut all these squares into triangles, then you can probably get a orthogonal mesh, right, that is also possible. So that means, let us say we have a mesh that is, we start off with a square mesh. Now I want to convert this into an orthogonal triangular mesh. Yeah, essentially I would draw this way, right, this would make it the mesh here, and then which way shall I draw? Either way is fine. This way, right, would it make an orthogonal mesh? Essentially you got these all should be parallel to the cell centroid directions, okay, and so on, right. We can do this. So these are some examples of orthogonal unstructured meshes. Fine. So let me pick one particular cell here. So that is essentially or two cells here. Let us say this one and this one. Okay. I am picking these two. Okay. and then we will look at how to discretize our equations on this particular cell. Okay. So, essentially one of this is the P cell, one of this is the neighboring cell. Okay. Let us call this is P and N. Okay. So, I am drawing only those two here. Okay. So, essentially that is a cell like this. Okay, that is what I have. I picked this P and N from here. Okay, so, this is what I have drawn here, which looks like this. I would like to call the primary cell, which we have been indicating till now as P, as some cell with subscript 0, C 0. Okay. Cell 0 is our cell P up till now, because right now we do not have any east, west, north, south. Okay. And then this C 0 cell, which is our primary cell, is now surrounded with how many cells? 3 cells, right? 3 neighboring cells, this guy, 3 face neighbors, right, and this one. Okay. But as of now I am drawing only one of the neighbors. We will extend the concept to later on to others as well. So, that means C 0 is surrounded by 1, 2, 3, 3 neighbors, right, C 1, C 2, C 3. I am as of now drawing C 1 cell alone, but we know that there are 2 more cells which are also orthogonal, right, which exist here, right, which I have not drawn here, but they do exist. Okay. So, I am looking at only these 2 components. Now, this is the phase vector, okay, and I can of course connect these 2 cell centroids C 0 to C 1, and this is one particular direction, and similarly this is my area vector A f bar, right, points in the direction away from the cell, right. So, this is now parallel to the line joining C 0 and C 1, as a result this is orthogonal mesh. Now, I can of course also define 2 coordinate systems. One is running along the C 0 C 1 direction, right, which I would like to call it as E xi, and another one running along the face, which I would like to call it as E eta hat. Okay. So, essentially these are, this is E zeta, E xi, E hat is, what kind of a coordinate system is this? Is it orthogonal or non-orthogonal? This is orthogonal by virtue of cells being orthogonal. Okay. So, because this line is parallel to the AF. So, this is a orthogonal system, orthogonal coordinate system. Of course, we already have our original orthogonal coordinate system, which was what? X y, x I hat, y j hat. This is also there. Okay. So, we have A f bar, fine, and let us define this distance between C 0 and C 1 as delta xi. Okay. Just like we had delta x between P cell and E cell, now we have 0 and 1, we will call it as delta xi. Okay. Of course, similarly you will have a C 2 cell here, C 3 cell here, and your definition for E xi and E eta would be different for each of these different combinations. So, for every phase you have a local coordinate system, right, in which xi is connecting the C 0 to C 1 or C 0 to C 2 or C 0 to C 3, and eta is in the direction of the face, along the face. Okay. Fine, that is understood, but as of now we will focus only on C 0 and C 1. Question still now, is this understood? Right. So, okay, let us move on. Then what is our governing equation? What do you want to solve? We want to solve steady diffusion, that is nothing but del dot gamma grad phi plus S phi equals 0, right, that is what we have. And what is the first step? Integration on the control volume. What is the control volume in this context? Which cell? C 0, right, C naught. So, that is essentially integral control volume del dot gamma grad phi dV plus integral control volume S phi dV equals 0. Now, we will invoke Gauss divergence theorem and convert this volume integral into a surface integral. So, this will be control surface gamma grad phi dot dA bar plus integral control volume S phi dV equals 0, right. And again saying that the gamma grad phi can be represented using the phase centroid value, right, as a mean value. We can rewrite this integral as a what? As a summation on all the phases. So, this can be written as sigma f gamma grad phi f dot A f bar, right, okay, plus we would say that S phi can be represented using its average value S phi bar, right, and we introduce a linearized model for the source term. So, this would come out to be S c plus S p phi 0, right, phi 0 is basically for C 0 cell times delta V naught, okay, that is delta V p. Fine. Okay, we have essentially we have not done anything different compared to the Cartesian coordinates till now, right. Okay, then let us go back and see what are these things. So, what is gamma grad phi f? Let us say I am taking one phase, okay. So, one of the phases. What is gamma grad phi? This is gamma f grad phi f. This can be written as what? Gamma f times I hat partial phi partial x plus j hat partial phi partial y evaluated on the phase, right. That is what we have in the x y coordinate system, right, that is fine. Then because my, so we have written in the global coordinate system, right, in this one. Now, because my local coordinate system, which is e xi e eta is also orthogonal, can I rewrite this gradient in that e xi e eta coordinates? I can, okay. So, what would that be? That would be gamma f e xi hat partial phi partial xi plus e eta hat partial phi partial eta. Is this one and the same? It is one and the same, right, okay. This is fine. Then what about my A f bar? A f bar of course has two components, right. It has some A x I hat plus A y j hat. It has some two components in the I direction and j direction. But can I also write this A vector in the local coordinate system? Let us say my magnitude is A f without the over bar. What is the direction which A f is pointing? E xi or E eta? E xi, okay. So, A f bar, let us say if it has a magnitude of A f, then what is A f bar? Can be written in the E zeta E eta coordinates as how much? A f E xi hat plus 0 times E eta hat. Can we write this? Right, basically the area vector pointing in the E xi direction with a magnitude A f, right. Okay, very good. Now, can we calculate what is gamma grad phi f dot A f in the local coordinate system? If you calculate that, what terms survive? So, E xi dot E xi would survive. Do you get any other term? No, everything else this is 0 and the dot product with this is 0, right. So, we do not get. So, essentially we will go back to our similar to previous way. So, gamma grad phi f dot A f bar would be how much? Would be gamma f E xi hat partial phi partial zeta E eta hat partial phi partial eta on the f dotted with A f E xi hat plus 0 E eta hat, right. This is the dot product and it will give you only gamma f A f E xi dot E xi, that is 1, right, times partial phi partial xi on the face f, right. That is what we would get, correct. Okay. So, this is nothing but gamma f A f partial phi partial xi f, right. This is for one phase that is connecting C0 and C1, right. So, we will get 2 more terms like this, each of them connecting C0 to C2, C0 to C3, right. We will get 2 more terms. What is partial phi partial xi f? Partial phi partial xi. So, essentially we are evaluating derivative in this direction. This is partial phi partial xi. What will be this? This will be value of phi at C1, that is let us say phi 1 minus phi 0 upon what will be the distance, delta xi. This is basically like our Cartesian thing, right, where we have partial phi partial x on the east face is nothing but phi capital E minus phi capital P upon delta xe, right. Okay. So, I can write this as a gamma f A f phi 1 minus phi 0 upon delta xi, right. Okay, that is understood. Now, do you see why we have actually written in the local coordinate system? Why not just work with the global coordinate system? Only to write this phi 1 minus phi 0, right, because our phi values are available only at where? At the cell centroid. So, we would like to have phi 1 and phi 0 to connect and calculate all the gradients, right. We do not want to do interpolations and then create another mesh on top of it, right. So, that is why we kind of introduced a local coordinate system for every phase, and then now we are calculating the gradients using the cell centroid values on this local coordinate system. Okay. Now, do you see a correspondence to the original Cartesian mesh case? What was the Cartesian mesh coordinates used to look like? What is the coefficients look like? Gamma delta y upon delta x times phi east minus phi p, something like this, right. So, what will be the coefficient now that we have? What will be the coefficient for A f, a neighbor? Gamma f A f by delta xi, that is the coefficient, and the corresponding f determines depending on the cell neighbor corresponding values. What will be the AP coefficient here, contribution to AP? The same value, right, same value will also go to AP and also will also go to the A neighbor. Okay. Fine. So, then now we understand that we will get 2 more terms, that is gamma f A f by delta xi f times phi 2 minus phi 0 and so on depending on number of neighbors we have, right. We will also get phi 2 minus phi 0 and phi 3 minus phi 0 and so on, right. We will get all these terms. Now, if we club all of these things, so we have original equation gamma grad phi dot A f f plus SC plus SP phi 0 times delta V 0 equals 0, right. We will of course want to write our equation in the standard form. What is our standard form? AP phi p, in this context phi 0 equals sigma A and B phi and B plus B, right. This is our standard form. So, what I am asking you is basically substitute gamma grad phi from here for each and every cell into this equation, right, into this term, and then rearrange it this way. Okay. Now, we have already gone through this. So, what will be A and B? What will be the coefficients? Of course, this will be the coefficient, right. So, this will be the coefficient, that means this is nothing but gamma f A f by delta xi f, and this f itself is defined for that particular neighbor, right. If you are looking at a neighbor of 1, 2 or 3, right, depending on that this f will be defined. There is no summation here, right. A and B itself is this value. This is like A east. A east is gamma delta y by delta x e. So, there is no summation here, right. But of course, N B can go from neighbors, that is 1, 2, 3 all the way to some capital M. If you have M neighbors, right, you do not have a triangle, you have some kind of a honeybee structure, right, some kind of a polygon, then you may have some 8 faces or 9 faces, right. So, depending on that, this f is defined. F is the phase between C0 and C1 or C0 and C2 and so on. Fine. Now, what about AP? what will all come in AP? AP is now has a negative coefficient, but it will go to the right hand side. So, what will this be? This will have one contribution. Now, you will get a summation, right. So, essentially you will get sigma A and B minus SP delta V 0, right. Your as usual SP term will be there. What about B? B is how much? SC delta V 0. Okay. So, the beauty is now we got a very simple equation which is the same as what we have got in the Cartesian, right, in the Cartesian mesh as well. Only thing is we just have now coefficients which we have to evaluate based on the faces. Now, can we calculate the area vectors if we know the mesh? Is it possible to calculate the area vectors? We know the mesh, right. So, when we know the mesh, we know all the coordinates, cell centroids, everything, right. Can we calculate the area? We can actually calculate, and then we can calculate all these things, right, and then work with this, fine. So, then let me make few comments, so that we can kind of finish this here. The comments are, so the assumption is that this is orthogonal, okay, orthogonal mesh. What we have also assumed is this is also a convex polyhedra cell. What is a convex polyhedra? What is a convex polyhedra, sorry? All diagonals. So, essentially any line connecting any 2 points inside the cell should entirely lie within the cell, that is a convex polyhedra, right. Now, why do we say we have to have a convex polyhedra for our case? That means we cannot have cells that look like this, right. Why is that so? Because if we have something like this, okay, somehow I have generated an orthogonal mesh, okay. So, we have a boomerang like this which is can give us some kind of an orthogonal mesh. Cell center will be outside, so what? Okay, we do not care why is cell centroid, if it is outside, what is the problem, right. Essentially it is not a representative of the cell values. What else? What else can go wrong? It will lead to negative coefficients, right. Do you see that? Once it is outside, all your calculations will lead to, the coefficients will all lead to negative coefficients, right. So, essentially that is why we cannot have, we have to have only convex polyhedra, right. We cannot have cells like this, because the cell centroid will lie outside if we have something like this. So, essentially it is not a representative of the cell values, okay. Is this treatment limited to 2 dimensions, this entire thing we have done? Let us say we generate a orthogonal mesh that is unstructured in 3D. Can I apply the same thing? We can do, right. Only thing is that you have more neighbors now, right. F will have, instead of if it is a triangle, if you have 3, if you have a tetrahedron, you will have 4, right. So, essentially this can be will work in 3D. So, you can probably have a tetrahedral cell, and this will work in 3D also, right. The same analysis can be extended. Okay. This will work in 3D. What about this equation that we have, gamma grad phi, this equation? This is a statement of conservation, right. You have the diffusion fluxes leaving the faces or entering the faces is balanced by the source term. So, we again still have the statement of conservation. Okay. So, as a result, the solution you would get is satisfies conservation. So, let us say if we have the source terms equal to 0, in the absence of source terms, is the phi 0 value bounded by the neighbors? B is 0, right. So, in that context, is it bounded? It is bounded because AP equals sigma A and B, this is 0, and AP phi 0 equals sigma A and B phi and B, right. So, essentially this is still gives you a bounded solution bounded by who? By the face neighbors, only the face neighbors, okay, not the other neighbors, not the ones which have a vertex in common, right, only the face neighbors. Fine, it is kind of bounded. Now, what about unsteady diffusion? Let us say if you want to solve this with an explicit scheme or an implicit scheme, can you do this? You can do this. Essentially, you just have extra term rho phi p1 and rho phi p0, right, that extra term. So, you can extend the entire unsteady thing we have done, the explicit, implicit and Crank-Nicholson to the structured, unstructured orthogonal mesh. Okay. So, we will not do it again. What about interpolation of gamma interpolation? Can we extend this to this mesh? We can extend it. Essentially, earlier you had this distances defined in the x direction. Now you have distances defined in which direction? In the xi direction. That's all. So essentially, you do that and this thing. What about the source term linearization? Is it the same as before? It is also same as before. So all these can be extended without any changes, right? Without any modifications of except for the geometry, right? Without any modifications can be extended. Okay, so far so good. How do you solve it? We got a system of linear equations. What method would you use to solve this? Let us say this is unstructured to begin with. Can we use Gauss-Seidel? Yes, we can use. So essentially, you can use Gauss-Seidel or Gauss-Seidel successive over relaxation, right? This can be used. What about TDMA or line by line TDMA? Can you use this? No, we do not have a structure, right? So as a result, we cannot use line by line TDMA, but of course, you can create some kind of a virtual line and kind of probably do it, okay. But the preferred method is Gauss-Seidel if you have unstructured meshes, right. So that is about it. So there is no assumption on structured, okay, no assumptions on structure. So essentially, you can have an unstructured mesh, but it only has to be orthogonal, okay. That is all we have discussed till now. Fine, okay, very good. I am going to stop here. We will meet in the next lecture. Thank you.